So thank you for this opportunity. I'm also proud to be here. And I would like to apologize that I can only show a representative selection of all the newest analysis we have, but you will also see some summaries. So that's something else you say? Okay. So that's for just for the laser pointer. All right. So this is the overview. I will introduce shortly the accelerator and the two experiments, CMS and Atlas, of which I'm presenting here a lot of results. First, standard model physics, then we go to Higgs boson physics, supersymmetry, and then I continue with more exotic searches and finish with heavy ion physics. And then I show some performance projections of the accelerator and the experiments. So first, about the accelerator itself and the experiments. So here you see the LHC accelerator, the 27-kilometer tunnel, and in particular here the two multi-purpose experiments, Atlas and CMS. Indicated here is the data flow. We have about 36% of proton run efficiency. Here you see the integrated and the peak luminosities for the different years. 2010, where we are running with a center of mass energy of 7 tera-electron volt. So this plots here, and then 2011 and 12. 11 also 7 tera-electron volt, and then 12, where we changed to center of mass energy of 8 tera-electron volt. This is this plot here. And this one where we accumulated over 20 inverse femtobarn integrated luminosity. And the newest results I'm showing are based basically on this 2012 data set. So this here is a CMS detector. You have first your inner tracking system. In the case of CMS and full silicon, then you have your calorimeters, and then the solenoid magnet for the bending of the charged particles to determine the momentum of the particles, and then outside you have 4 layers of muon chambers embedded here in iron, which is the return yoke to focus the magnetic flux inside the detector, and then you have a stronger magnetic field. And similar, the Atlas detector, if you compare it, it has 4 to 5 times the volume of the CMS detector, so that's the biggest detector in the world. Here you see the hardware performance of the different subsystems and subdetectors of CMS and Atlas detectors. And the good news is that on average we have 98 of the channels are operational. That makes it easier for the reconstruction and comparison of our data to the simulation. Now here you see the scale energy flux of the particle as a function of the particle energy. So that's presumably more familiar to you than to me. I only have indicated here translated into the center of mass energy for proton-proton collider here, where we see the LHC energy and reach. Here you have the kinematic plane in virtuality and proton momentum fraction x, and this is here the reach of LHC, and then indicated here is also the Auger kinematic limit. And here you have a large phase space area at low proton momentum x, which means forward physics and also diffractive physics, and then also at a low virtuality here, which corresponds to non-perturbative physics, in particular underlying event. When you look at diffractive physics, that means that you have a colorless exchange between the two protons. In this case here, single diffraction, where you have here a rapidity gap without activity between one proton which stays intact, and then here the hard scattering, where you expect jets and other particles flying into the detector. Then you can have here a double peron exchange, where you have 2 rapidity gaps, and here a double diffraction, where you have then a rapidity gap between the 2 protons, and then the hard scattering of the 2 protons in forward direction. So this is the CMS experiment, where you have also implemented here the totem experiment, which consists of these telescopes here, T1, T2, and then you have also Roman pods, which cover the very forward region. Here you have the pseudo-rapidity ranges indicated. And then I'm going to show you 2 example analyses, which are covering this phase space, which is also interesting and important for astrophysics. So here you see the pseudo-rapidity and leading transfer momentum distributions of charged particles. This year is with the central detector of CMS, and this here is then with the totem telescopes, which is being measured. And here you see the transverse momentum distribution of the leading jet. And here you see also for different experiments, starting here with UA, also LS and CDF, and then the latest CMS experiments here, which is with non-single diffractive enriched, which means that you expect tracks in both T2 telescopes of the totem experiment. This here is another example where you measure here low transverse momentum inclusive jet cross sections, which you are measuring in the forward region. And this was here a dedicated particular run. You see a low luminosity where you had a little amount of minimum bias events, so low pile-up conditions. And then you cover here the low transverse momentum energies between 21 and 74 GeV. And here you have indicated then the differential cross-section in 7 different rapidity bins. And both are in good agreement with predictions from theory compared to next to leading order calculations. Then I come to standard model physics. This is differential inclusive jet cross-section. So that's the right part we have already seen in the plot before, but that's now perturbative in the central part of the detector, which is in 6 rapidity bins. And again, you see a comparison here, superposed next to leading order. It's in good agreement. When you show the data over theory ratio, you can try to distinguish for different pattern distribution functions. And here you see it for neural network PDFs, which are in good agreement with the data. And here you have another example of ABM11 PDFs, which are excluded by this measurement already. This here shows you a multi-jet cross-section measurement from Atlas. This is the ratio of the 3-jet to 2-jet inclusive cross-section as a function of the leading transverse jet momentum. Again, in agreement with the data, and then you can extract alpha S for the relatively high transverse momentum jets. And here you see then all the different experiments and the world average indicated, which is consistent with the newest measurement of Atlas, which goes here to the highest virtuality scales measured yet for alpha S. Here you see summary plots from CMS and Atlas of vector boson and top pair production. And again, everything is consistent with the standard model expectations. You have an example of ZZ production cross-section. What you see in this plot here is the leading lepton pair invariant mass to the sub-leading lepton pair mass. And like the data points, consistent the distribution here with a simulation with 2 Zs and 4 leptons. And here you have the latest measurements from Atlas, which is on this curve here for PP collisions, and this here is for PP bar collisions, where you have also the old measurements of Tevatron. Again, it's in very good agreement with standard model expectation. Then one interesting thing, you can look at anomalous triple and quartic gauge couplings, which you see here indicated for different experiments. And you see it's all consistent with the standard model so far. There are further couplings, WZZ, Z gamma gamma, ZZ gamma, and triple Z. I cannot show here, but they are all consistent with the standard model expectations. So now I'm getting to heavy flavor physics. And I'll show you first here our dedicated diamune triggers, which enhance the statistics, in particular interesting for J psi's, B sub S, and also upsilons. And here you have one measurement from Atlas where you measure B sub S into J psi phi. And from this measurement, you can then extract the decay with difference between the light and heavy states and the weak phase phi S. So here you see the invariant mass distribution, your reconstructed signal here when it's subtracted background. And here you have the proper decay distributions of the particles, and here you have then the extracted decay width difference as a function of this angle phi s. This is a standard model prediction, and the measurement is consistent with the standard model. And the interesting thing for this measurement is that this angle phi s is related to the CKM matrix angle here, this minus 2 beta s. And the prediction of the standard model is that this value is small. And so you hope if there would be new physics, which you could recognize indirectly, it could contribute into loops, and then cause here a higher value of this angle phi s. But right now it seems to be consistent with the standard model. And now I'm coming to the B sub s and B sub d into mu plus mu minus pair measurement from CMS. So it's also interesting because this decay mode is highly suppressed in the standard model, and then you measure the branching ratios of both B sub s and B sub d. Again, it looks to be consistent with the standard model. Here you have 30 years of history of these measurements, and here indicated are the standard model expectations. And right now we have reached here the standard model cross-section, and we have here a first measurement from CMS with 4.3 sigma and a smaller significance for B sub d decay. And when we combine this measurement with the latest measurement of LHC, then we get even the observation of this decay channel, which is consistent with the standard model expectation. For B sub d, it's not yet statistically significant. Here you see a compilation of different experiments and measurements for B sub s and B sub d. In green here is the expectation of the standard model. And at the bottom here you see the latest measurement of the CMS plus LHCb combination. Then we come to top quark physics. So TG bar production is dominated by gluon-gluon fusion, about 90% at the LHC. And you have the diagrams of single top production dominated in cross-section by the T channel. Then you have here the TW channel and the S channel. So what you see here are the latest measurements from Atlas for single top production cross-section. Again, you see here this is the theory prediction for PP bar. For a proton-proton, and this here is PP bar, so that's indicating here the Tevatron old measurements from Tevatron measurements. And here you have the latest Atlas and also the previous Atlas measurement combination. And here from CMS in comparison to next to leading order approximated, and we are already in possession of the full next to leading order prediction that will increase the accuracy. So we have only here an uncertainty then in the future of 4%, which allows to probe the gluon density inside the proton. Here you have an example of a jet shape measurement from Atlas, which gives you information of the flow momentum distribution inside the jet around the jet axis. And the basic information you extract here is that the light quark jets are narrower in this distribution compared to the B quark jets. You have single top production cross sections in the different channels from Atlas, and here you have from CMS the measurement of top versus anti-top single top production. This is the measurement, and here you have the theory comparison for different pattern distribution functions, and that's also consistent with standard model expectation within the errors. So for the T-channel single top production measurements, we reach uncertainty between 30 and 19%, and for the matrix element VTB is about 10%. Here you have compilation of top mass measurements from CMS and from Atlas, also indicated here the Tevatron combination. And the good news is that we are reaching the Tevatron precision right now, so the systematic uncertainties go below this 1 GeV threshold. And there are many other experimental results, but this is too much for today. Can only invite you to show at the public physics results webpage from Atlas and CMS. Now I come to the Higgs standard model Higgs analysis. So the dominating cross-section you have from the gluon-gluon fusion processes, and then you can have Higgs radiation with a vector boson, TG bar fusion, and also WZ fusion. So here you have the Higgs production mechanisms. The yellow line here indicates where we have measured a new boson-like particle. This here shows you for the different center of mass energies of the LHC accelerator how the cross-section evolves. Here you have the different decay modes, branching ratios, and this here is splitted for the different di-boson decay modes, which each have a separated analysis channel. In this table here you see the analysis which are pursued. The most prominent ones this year, Higgs into BB bar and tau tau, they have the highest number of events, but they have also the largest background, so the signal over background ratio is rather low, and the mass resolution is not very good. So this measurements used typically for measuring couplings and branching ratios, but when you want to go to discovery and the high mass precision measurement, then you go here to Higgs to gamma gamma and Higgs to Z bosons, where you reach here a mass resolution at 126 GeV, where I found the particle of 1 to 2%. There are further channels which are being analyzed, but these are the dominant ones in the blue table. And here you see an example analysis. This is a measurement of Higgs boson into Z bosons, and then for leptons, and you can clearly see the signal, so the local significance of this signal here corresponds to 6.7 sigma for this single measurement, and the signal strength is consistent with the standard model expectation. And here you see a plot to verify the spin parity of the particle. So this here in orange is for a scalar boson, which is favored, and a pseudoscalar boson is disfavored, as you can see here. So the red arrow here is indicating our measurement at CMS. And also a spin 2 hypothesis is strongly disfavored. And furthermore, this range here from 130 to 827 GeV is excluded. So we are not seeing there any further standard model Higgs boson-like particle. Then you have here another example. This is a Higgs to gamma gamma channel from Atlas, where you use a boosted decision tree and distinguish the 3 different production mechanisms here. And then you combine the results afterwards. And here you have the invariant mass distribution. Here the background subtracted. You see this clear signal. And here the local p-values from the measurements 7 TeV, 8 TeV, and also the combination. And that gives you here local significance of 7.4 sigma. Then you see here some results of the signal strength couplings. So this is for the different decay modes of the Higgs boson, and all these measurements indicate here that it's consistent with the standard model. You have the different coupling strengths times the branching ratio. You have here 3 different measurements indicated from Higgs, and all are consistent with the expectation of the standard model, which is indicated here. And here you have coupling strengths in the 2 fermions and vector bosons, and again it indicates that it's consistent with the standard model expectations. So here I'm showing you projections, what we would be able to gain in accuracy when we go to 300 inverse femtobarns at center of mass energy of 14 teraelectron volt. So the large green bars you see here for the branching ratios of the Higgs, and here the couplings. This is from ISHAP 2012 for status of the analysis and performance. And then you see that we could shrink the errors by a factor between 2 and 4. It depends on the particular measurement. But that's what we expect to improve when we increase the statistics when we start in 2015 again with the LHC. So now I'm coming to supersymmetry. First, the phenomenology. So we have the typically heavy flavor jets, leptons, taus, photons, and visible typical lightest supersymmetric particle, which gives rise to missing transverse energy. And that's in the parity conservation models. And you can have, of course, also a parity violation where the LSP will decay. And then you can have also search for long-lived particles, for example, if the couplings are weak, as in the case for apparent violation, gravitino, and mass degeneracy, where you can have then particles which decay after a considerable amount of time, and that would be resolvable then hopefully in the tracker volume of our detectors. Here you have the different production modes. The cross-section, it's dominated here by particle pair production. So this is one big industry of search. And then you go here to the next biggest. This is third generation search for squarks and also leptons. This is natural SUSY driven. Where you look in particular to stops and sputum production directly or via gluons. And then the lowest one is here electroweak production, where you look for gauginos and also leptons. And all these different channels you can assume apparently conserved or violated, and also prompt or long-lived particle decays. And I show you two example analysis. So this one here is from CMS. We have bottom and stop production, where you have then in the final state here heavy flavor jets. Here you see an example event where you have there 5 jets and then a few of them B-tagged. And here you see the exclusion limits in the plane of the lightest neutrino as a function of the gluino mass. And the same here for the stop search. And you see that we can set limits here which go slightly above the tera-electron volt channel. This here is a search for charginos from Atlas. An interesting analysis where you assume almost a mass degeneracy with the lightest particle. And then the chargino has a considerable lifetime, and it's expected to be decaying in the tracker volume. And then you have here a typical disappearing track signature. And that's what you are looking at. And here you have the exclusion limit, the decay time as a function of the mass of the chargino. And that's what is excluded here in this area. This here is a summary of different supersymmetric measurements. This is here for direct stop production. Here you have electroweak production. Here you see for gluino production. And here in the M-Sugra plane, M1/2 versus M0, all the different measurements and the phase space which is already excluded. And here you have a summary. So it's plenty. These are all the latest measurements we have. It's too tiny to recognize something, but you can look at it on your laptop. And if you go to the web page from Atlas and CMS, then you can find this and also all the measurements. Then I come to the exotic measurements. This is a search for dark matter in the mono-lepton channel. So the idea is here to have a dark matter pair candidate which is produced, and then you have a W boson which decays leptonically. And then you can have here also this Feynman graph. And in this model is not fixed the possible superposition of the two Feynman graphs. So you have here psi, which in the models considered here can have the interference values -1, 0, or +1. And here you have the transverse mass distribution. And then you see superposed here over data and the standard model expectation, the 3 different models and values. And then you have here exclusion limits for the energy scale lambda as a function of the chi mass. And at the bottom here you see for spin independent the chi nucleon cross-section limits as a function of the chi mass. This is this measurement here. This is another mono jet measurement which is stronger, and then you have a dedicated experiment limits indicated. This here is another experiment to the result from Atlas. Dark matter pair production. So again you have here a dark matter pair, and then you have the W boson which is supposed to decay hadronically, and it strongly boosts. So basically you are looking for 1 jet in your event. And then you have here the distribution of the invariant jet mass, again data compared to simulation, standard model expectation, and then here different models, D5 operators here. And then you see here again exclusion limits, the chi nucleon cross-section limits as a function of the chi mass. And this is here for the D9 operator, the observed limit, and then again other experimental results here indicated. So this is a search for microscopic black holes. This is a dimuon channel where you look for like sign dimuons. So the muons allow you to reduce strongly the multijet background, and then dimuon like sign allows you to reduce strongly TT bar and diboson production background, for example. And then you have here the distribution of the track multiplicity, and then indicated here a possible model signal. And here we have an exclusion limit of the black hole threshold mass as a function of the fundamental Planck mass. And then you have here excluded because the fundamental Planck mass has to be below this threshold. And then you have here the different limits for different extra dimensions. So these are again limits of all the exotic measurements, this time as an example here from the CMS results. In particular here, contact interactions, you see the limits on this energy scale lambda go up to 14 TeV. So last topic on analysis here is heavy ion physics. This here are two particle correlations where we look at long-range near-side angular correlations. Here we have the plots are indicating the azimuthal angle difference between the two particles and the pseudo-rapidity difference between the particles. And you see here this typical ridge that's for lead collisions and for proton-lead collisions, where it's more pronounced, and the findings might help to get a clearer picture of the earliest moments of the universe. And the present understanding is that this, what we are seeing here, is a consequence of an explosion of a droplet of quark-gluon plasma. This here is a measurement from ATLAS, where you go beyond two particles. You have multi-particle azimuthal correlations, and you split it in 6 bins of transverse energy sum into the lead beam direction. And then you see here, let me just pick out this example here with a second-order harmonic. Here's the data. The different models are apparently able to describe the shape more or less, but you see that the data is much higher. And that's evidence for the importance of the final state effects in proton-lead collisions. So then I come to the prospects. This is a timeline here. Right now we're on the long shutdown 1. And April 2015 we are expecting to start again. And then we will switch from ATV to presumably 13 teraelectron volt center of mass energy. And then we are running until 2018, where we have the long shutdown 2. And we are going to reach then the nominal luminosity. And after the long shutdown 2, we are doubling then the luminosity. And then we start with the so-called phase 2, where we want to improve the luminosity with a high luminosity upgrade of the LHC further, where we then hope to get 250 inverse femtobarn per year. Here you have an example of level 1 trigger upgrades. So you see here 2 scenarios, 50 nanoseconds, which we were running until February this year, and then in the future, presumably, we are going to switch here to 25 nanoseconds. Then you see improvement of the upgrades compared to what is installed now for the different Higgs decay channels. So this here is the high luminosity upgrade, where we are continue running in the LHC tunnel, starting presumably in 2022, and then we will expect about 10 times more Higgs bosons. Center of mass energy is supposed to be 14 teraelectron volt, but we will have 5 times more luminosity as we will have when we start in April 2015 again. And here you have some simulation examples, what we expect with 3000 inverse femtobarn in this high luminosity run. You can handle here the rare signal channels like TTH, for example. Here you can see the signal, or here Higgs into muon. Here the expected background subtracted, where you can really see something. And also vector boson scattering, which is interesting because unity would be violated if there would be no damping from the Higgs, but there could be additional damping from new physics. And therefore, it's interesting to check here for resonances at the TEF scale. This here is high luminosity for Higgs. So we have here the different Higgs decay channels, and this here is comparing the decrease of the errors when we go from 300 inverse femtobarn to 3000 inverse femtobarn at this high luminosity configuration. And this here is for the partial decay widths. So there's a lot of improvement to be expected. These are prospects for a high energy Large Hadron Collider. So you would use the same LHC tunnel again, but you would increase then the center of mass energy to 33 tera-electron volt and the same luminosity. And therefore, we need to have 20 Tesla dipole magnets in the tunnel. So the limitation right now is not the acceleration. Actually, we could go to higher energies, but we are not able to keep the particles in the ring. So therefore, we would need to place there in the tunnel stronger magnets. And then beyond, one possible option would be the very large hadron collider that could be an 80-kilometer tunnel in the Geneva area. So this here is the LHC tunnel. And then we could reach here an energy of up to about 100 tera-electron volt. Thank you.
Okay, so we have time for a few questions, if there are any. Yep.
Yeah, do Atlas and CMS have measurements of B0 to K-star gamma gamma? You know, LHCb has this strange angular distributions for the decay products.
I know that there are, the last couple of days, there came a new measurement out, but I think it's not with gamma gamma.
Sorry, mu plus mu minus is what I mean. Sorry, K-star, mu plus mu minus.
Yeah, there the last days there came a new measurement out. But it's, I have to check if it's still preliminary. Might be that I saw the email yesterday or 2 days ago.
I mean, I think it's LHCb that sees this strange angular distribution, so I wondered if it confirms those or not.
Yeah, there's no statement yet, as far as I know. These are complicated analysis where you have time-dependent angular analysis, and that needs typically a lot of understanding. And you see this also in this Atlas analysis we have seen. It's very complicated where you have three-dimensional phase space for the fitting, and a lot of things need to be understood before you can really be confident that what you're measuring is not a technical particularity of your fitting procedures. But as far as I know, there's, so either it came out eventually Saturday, or you have still to wait. In general, I think Atlas has less handle to measure this because they don't have this inner tracking system in silicon. You see here also the Atlas measurements are typically worse and behind from CMS. This is a very complicated analysis.
Yep.
Do you have a more general sense of where the field's heading? I mean, I noticed that you had a timescale. You know, you have a timeline through to 2030, and then presumably beyond with regard to the VLHC. And I mean, that's reaching the point where we have a timescale that's possibly greater than the career of the average scientist in the field, in terms of how this is mapped out. And I was wondering, you know, I mean, if you really wanted to do something, I mean, is this a sign that accelerated technology, in some sense, you know, can't be scaled indefinitely? And where would you see the field going next if you wanted to get to really high energies? I mean, is there any? I mean, what would be the the more disruptive technologies that might allow us to pursue these things at, you know, greater energies than, you know, sort of, you know, hundreds of TeV potentially?
Yeah, beyond hundreds of TeV, there's a big industry for improvement of accelerator technology, that you don't need 30 kilometers, but you could do it maybe on a few hundred meters. And that's ongoing, in particular in the United States, where they have now shut down the most leading accelerators at SLAC and at Tevatron. Beyond that, one big improvement would also be if we would have high temperature superconductivity for macroscopic magnets. When you have it in the laboratory for small pieces, but they behave like porcelain, and you cannot build their 15-meter long magnets. And if we would have that would life and budget, that everything would make life easier, because we wouldn't need this expensive helium anymore. Right now at CERN they have about half the industrial available helium resource for the 27-kilometer fridge.
So the helium, in fact, is the limiting, I mean, it's the sort of rate limiting step at CERN as much as anything else.
So concerning the acceleration, the limitation is the strength of the dipole magnets. And the point is, of course, every year it improves a little bit, but it would not be worth the effort to replace now the 8 Tesla dipole magnets by 9 or 10 Tesla dipole magnets. So you have to wait until the technology, we are able to achieve 20 Tesla magnets, and then you would replace it, because it would take another few years shut down. Because in 2001 they have stopped with a large electron positron collider, and in 2008 the LHC has started, so that's not something which you can do in half a year or so.
Okay, so let's thank Lars again.